Let's look at example 1. So here we're going to be working with the equation x squared plus y squared equal to 4. So that same curve we looked at, the circle of radius 2. And in this problem, we're going to be viewing y as a function of x. And we know that because we're interested in this derivative dy dx. So the fact that we're calculating dy dx here tells us we're viewing y as a function of x. So again, the symbol that we see here, the dy, tells us we're interested in differentiating function y, and then the fact that there's an x here down here tells us that we're interested in differentiating y with respect to x. So we're treating x as our variable. All right, so we have this equation. We're viewing y as an implicitly defined function in terms of x. We don't actually know what y is equal to. And so we're going to calculate dy dx using this implicit differentiation technique. All right, so let's kind of look at the steps here. Step 1, we're going to differentiate both sides of this equation with respect to x. So really what we're going to do is we're going to apply the derivative to each term. So let's do that. That's step 1. So let's write down our equation. X squared plus y squared is equal to 4. And we're going to apply the derivative to each term in this equation. Both sides of the equation. Applying the derivative to everything. And we know from our derivative rules, where we see a plus sign here, we can split up that derivative process. All right. So now we go through and we look at each of these individual pieces and see how to differentiate it. So this first one, there's only an x term. So this only has an x term. So how do we differentiate that? Well, for a term involving only x, we're just going to differentiate it like usual. So all of our usual derivative rules are still going to work here. So what that means, derivative of x squared is 2x. Usual power rule here. Okay. What about this y squared term? So this is a term that only has a y in it. So how do we differentiate something like this? It's a two-step process. So for a term involving only a y, we're going to differentiate it like usual. So that's kind of inherited from the variable part. But then we're also going to multiply the result by y prime because we're also viewing y as a function. So there's kind of a hidden chain rule going on here. So we have this y squared, and we're going to do two things. We're going to differentiate like usual, and then we're going to multiply by y prime. So what would this look like? What's the derivative of y squared? Well, 2y. And then we multiply by y prime. So we've differentiated like usual to get the 2y, and then we multiply that result by y prime. And then on the right side, we're doing the derivative of a constant 4. Derivative of a constant all by itself is going to be 0. All right, so we've differentiated both sides of this equation with respect to x. Kind of went term by term and differentiated each of those using our regular derivative rules with this slight wrinkle when we had this term involving only y's. All right, so this y prime here, this is what we want to solve for. So y prime is our dy dx. And if you wanted to use a dy dx here, you could. So we want to solve for y prime. And so the way to do this is step 2, we're going to move all y prime terms to the left side. And then we're going to move all the terms without y prime, we're going to move those to the other side. So let's get all the y prime terms, keep them on the left. And then we're going to take this 2x. There's no y prime in here, so we're going to move it over to the right. And when we do that, it becomes negative. We subtract it from both sides. So we have 2y times y prime is equal to negative 2x. If there was more going on here on the left, then we might actually have to factor out a y prime. But we want, essentially what we want, let me rewrite that. We want to solve for y prime. That's what we're trying to do here. And that's what really these last steps are doing, is solving for y prime. So we're trying to get all the terms with y prime by themselves on the left. If we needed to, we could factor out a y prime. Here, it's kind of already factored for us, seeing how there's only one term. And the last step then is to actually get y prime by itself. So we have this 2y in front. What we're going to do is divide both sides by that term. So we're going to divide both sides by 2y. And when we do that, we get y prime is equal to negative 2x over 2y, or negative x over y. And so there's our derivative. There's dy dx. So, we could use just a little comment on the notation here. We might be using dy dx. Same thing as y prime. So if you want to use primes, or if you want to use dx's, just some of our different notations here for how you might want to represent that. So first step, differentiate all the terms of your equation. And then once you're done differentiating, then work on solving for y prime. So here we have our derivative y prime. It's negative x over y. And notice when you actually get this, we actually didn't have a formula for what y was equal to. So when we actually find y prime, it should most likely is going to involve both x's and y's, and that's perfectly fine. All right, so part 2 to this is once we have our derivative, we can use it then to play all the usual games. So we can find the slope of our tangent line, we could find the equation of our tangent line, things like that. So in part 2 here, we're going to find the slope of the graph, or the slope of the tangent line, at this point 1 comma square root 3. And so how is this going to work? Well, slope of the graph is just the slope of our tangent line. You can kind of see it all graphed here. We actually have our curve. So this is x squared plus y squared equal to 4. So it's a circle of radius 2. We have our tangent line drawn in. And then this is the point that we're interested in, 1 comma square root 3. All right, so the slope of our graph is the same thing as the slope of the tangent line. And the way we actually calculate this is it's our derivative. And we're going to evaluate our derivative at this point. So it's going to be our derivative evaluated when x is equal to 1 and when y is equal to square root 3, because those are our two coordinates here. And so if we remember, what did we find for the derivative? We had a nice little formula we found. We found the derivative was equal to negative x over y. So when we evaluate this, wherever we see an x, we're going to change it to 1. And wherever we see a y, we're going to change that to square root 3. So when we plug in, instead of being negative x over y, it's going to be negative 1 over square root 3. Or if we wanted to rationalize this, negative square root 3 over 3. Either one's fine. And you can see that's certainly plausible because this tangent line is pointing downward, and that kind of agrees with the fact that this is a negative slope. All right. So we're just going to try a few more examples of these, look at more complicated equations and see how to calculate dy dx using this implicit differentiation.